Okay, so I will be sharing this on Brightspace later, as long as that's okay with everyone here. I'm pulling up the chat, so if you raise your hand or ask a question, I can see you, but also feel free to unmute. So we're going to look at this problem here where we have a force applied at B. We have link AB vertical in this particular moment, and OB is a length of 800 and point B is 400 below the axis. And so we're going to evaluate buckling. So which pin here, no, which link here is in danger of buckling? Which link are we going to analyze?
Diagonal.
Which one? The diagonal one you said?
Yeah.
Yeah, exactly, because the perpendicular link is not in danger of buckling. It is not loaded in the axial direction at all. And so first steps here, what are we going to do? Can't hear you, Jasper.
About this.
Yes.
Excellent. The statics portion of figuring out the load in the axial direction of that link.
Okay, so we're going to do our statics to figure out what the load is. Yes. So on we go. So we have OB, we have AB, we have a force, okay, and so I'm going to briefly do this piece, but I'm assuming that this is not what we need the review on. So we separate our links. We have OB and AB, and that marker is not happy. So we have OB and AB. We know OB is going to be in compression because we're looking at buckling, which means it's acting equal and opposite there at B. We also have our reactions at A. So this is my AY, AX, F, FOB, FOB, FOB. Okay, and so if we sum the moments about A and set it equal to 0, we get an answer for FOB. So that's our statics, right? So very brief, making sure we're all on the same page there. I am going to throw numbers out into the world today because it will help us actually perform the analysis here. Okay, so they are relevant. What's not relevant is the number crunching, so I'm not gonna fuss about that. But as we solve here, okay, sorry, there was a discrepancy in my notes, but so FOB turns out to be about 1.4 kilonewtons. Okay, so we're just going to put a pin in that. Now we're asking, what we're looking at is there out of plane buckling? Factor of safety is that's what we're looking for. So our very first step is always to evaluate statics. Now we know the load on the link in question. What next? What are some things we need to identify or know or investigate? Like, what is the next piece of buckling work? The slenderness ratio, Robert, exactly. And in order to determine the slenderness ratio, as I look at this, one of the things I need to know is how it's fixed on either end. And so for out of plane bending, it tells us that the pin joints are constructed with sufficient size and fit to provide good resistance to out-of-plane buckling. And that is a very intentional and specific sentence. So what is that sentence telling us? What do you think? It is there right above the PowerPoint as I try to find the right slide here.
I think that what that's saying is that essentially the ends are, quote, fixed in relation to the bending that we're looking at.
Exactly. And so as we look at our end conditions, we can see that if it wasn't sufficiently fixed, we would have a different end condition constant than if we could assume it was fixed at both ends. And so this gives me a recommended value, fixed gives me a recommended C value of 1.2. And so we'll go ahead and use that. Any questions there? Okay, so then let's evaluate our slenderness ratio. We have two to calculate. So let me bring my camera back. So we have two slenderness ratios to calculate. We know our force, and I'm going to go ahead and start tabulating what we know. So we know that the length is 800, we're probably in millimeters here, yeah. We know that our end condition constant is 1.2. In order to know my slenderness ratio, I'm going to take the length and divide it by the square root of the radius of gyration, which is the inertia over, I'm sorry, the length of the radius of gyration, which is the square root of inertia over area. And then, Jasper, exactly right, we also need to find that critical ratio, which is not a function of geometry, but rather a function of the material and the end conditions. So let's go ahead and find that expression here. Okay. So our critical slenderness ratio is 2 pi squared end condition constant modulus of elasticity all over the yield strength, and then we take the square root of that. And that gives us this point here on our curve, which helps us determine if we're in the slender region, in the Euler curve region, or in the not slender region, the Johnson or parabolic curve. Okay, and so we evaluate the geometry and we evaluate the material properties, right? So a material that's not as strong or a material that's very elastic will be more likely to buckle, right? And that's material properties. In terms of geometry, if it's very, very long, or regardless of its length, if it has a very small cross section, so it has a small cross-sectional inertia and area, then it will be a more slender geometry. So so we're going to compare these. I think I lost my train of thought there, but we're going to compare these. We're going to take the 800 millimeters. We're going to calculate our inertia and our area and get some values for both of these. We know C, we're dealing with steel. And so so we're going to use 200 megapascals for our yield strength. And a modulus of 207 gigapascals. I know our cross-sectional area, I believe it was given to be 20 by 10 millimeters. Please stop me with questions as you have them. So I know that it's width is 20 millimeters and thickness is 10 millimeters for our rectangular cross section. And so that's all the information I need.
Is width in that dimension like vertically in the direction that it's shown on the picture?
Yeah, that's a good question. So
And
if my
thickness
link,
is in to the page?
yeah, exactly. So
Okay.
this is width, which means thickness is perpendicular to that. Yep. So if we think of our BH cubed, if I is equal to 1/12 BH cubed, then I over area is 1/12 BH cubed over BH, right? So that'll go away and that becomes a 2, those cancel. And so this is H squared over 12.
Can you go over how you're defining the B and H on those? I'm just not seeing in my head why it's that way.
Oh, it's because it's out of plane. So it's wide and thin and it's bending out of plane. So the base is the width and the height is the thickness. Right, so if I was to look at this cross section, I'm looking at HB.
I literally just drew out the same thing on my own whiteboard. Thank you. Yes.
I'm glad we got to the same point.
Would we reverse that if we were looking at in-plane bending?
No, it would not.
Okay.
Let me try to wrap my head around that one now.
Wait, it wouldn't?
I don't think so, because it's not bending in the same direction. So then it's bending.
We didn't, whoever that was just talking, say you would reverse it?
What? Oh, that's what I was saying. Yeah, I think it reverses.
Oh, I think
Okay,
that's what I
yeah.
heard.
That's
And
what
that's
I
what
heard.
I was
Oh.
questioning. Okay.
It wouldn't be the same. It would be reversed, right?
Yeah, okay. Yeah, that's what
Excellent.
I asked.
Okay, okay. Sorry, I misheard you. I thought, yes, if it would be the same. Okay, so in this particular case, the width is the base, the thickness is the height, and our inertia is base height cubed over 12. We're really looking at K, which is the square root of IA. And so, it all simplifies down is what I'm trying to explain. Wesley, I just saw your chat and I'm recording today. So the good news is no worries if you miss a little bit because of connection. And that also means, folks, if you can hear my background noise, please do tell me. Okay, so I know how to find my slenderness ratio. So now I'm going to take L over the square root of, well, it's just H over the square root of 12, isn't it? So H over the square root of 12, and this gives me a number. Hooray for numbers, 277. Okay, so now I know the slenderness ratio of my actual link. So that's the physical link that's on this system. What I want to know then is what's my critical slenderness ratio. So I'm gonna plug in the 1.2, 200 for the yield strength, and 207 times 10 to the 3, right? So here, so we'll plug in and evaluate these numbers. Again, I don't think that's the interesting part here. So 157. If there is a piece of this that is mystifying though, please do speak up. So I now have my slenderness ratio for the element and the critical slenderness ratio for this material and end condition scenario. So is this a slender or a not slender link? right? So we're going to compare L over K to our critical ratio, and we see that it's bigger. So have we moved right or left on the curve here? So, right, exactly, yes. Yes, slender. Okay, so we're in the Euler curve. So now I need to know what my critical loading is on the Euler curve. And so I evaluate for my critical force that causes buckling. So that P critical here is the load at which we can expect buckling. Okay, and so C has not changed. E is still the modulus of elasticity. Our slenderness ratio hasn't changed. So we're going to take and evaluate the critical force by multiplying these quantities by the cross-sectional area. And so we get a load of 6.4 kilonewtons. So was everyone followed to this point? The piece that would change if it was less than the critical is we would use, instead of Euler, so this is Euler. Instead of Euler, we would use Johnson's. I appreciate the feedback in the chat, folks. Keep it up.
And am I remembering that our actual load is somewhere around 1.4
That's correct.
kilonewtons?
Yep.
Okay.
Yes. And
You
so
said, sorry, you said instead of Euler, use Johnson?
if, so, okay, so let me fix my notation here. So blue is Euler. If this was less than the critical, use Johnson.
Right.
Okay, just making sure I'm clear here.
And that is a slightly different formula for the critical force.
It is. And so what we'll see is with Euler, it's entirely a function of the slenderness ratio, which as that goes up, the critical force comes down, right? And then how flexible is it? So if it's less flexible, if E comes down, the critical force comes down.
That doesn't make a ton of sense
Yeah,
in
hold
that
on.
wording there.
Yeah, no, I don't like the way I worded it. That's why I got stuck. So as the value of E comes down, that means I have a shallower
Increasing
slope?
flexibility, right? Less
Mhm.
stiff. I don't know. I'm hurting.
Oh, yeah. So as the value of E is lower, it takes less stress to induce more strain, and so it is more flexible. A lower E is more flexible, which means at a lower critical force, it will buckle. Ha, okay. And if the cross-sectional area comes down, your critical force goes down, it's easier to buckle. And as your C goes from 1.2 to 1, easier to buckle. So this is 100%, like it's really easy to see where the buckling is affected by flexibility and how slender it is, etc., right? If I look at the Johnsons, it's much more a function of strength. Because if it's short and stout, then we're looking more at a failure of strength. So, I mean, yes, slenderness ratio is still in there. C and E are still in there, but I also see that there's a strength that isn't accounted for in the other scenario. The other one is only looking at how slender it is and how flexible it is, right? Really?
Interesting. Thank you.
Yeah, absolutely. Yes, Ryan, exactly. In buckling, it's, I mean, we could certainly say P critical over area is the axial stress, right? We could do that, but because it's in term of that critical load, we'll go ahead and just directly apply the critical load together to see the factor of safety. And that didn't come out in super clear English, so let's just do it. So what we have is we know that our loading is about 1.4 kilonewtons and our critical load is 6.4 kilonewtons. So then our factor of safety for buckling will be the ratio of those, which is like
It's 4 and change.
yeah, right. Oh, actually, it's a little bit high. So it's like 4.5 ish.
Is there a general range for factor of safety that's like used, or do you kind of just like make it up determined on the situation?
It's very much It's very much contextual. And as we start talking about failure theory, we'll see how the different failure theories also give us a different understanding of what that factor of safety might be. If things are stationary, factor of safety is not necessarily as important. You might be wasting material, but you're not trying to move something. Now, if you're trying to move something and you're using energy to do so, increased factor of safety equals increased energy consumption. And better yet, if you're trying to get it into the air or into space, increased factor of safety equals less feasible. So it depends on your context, right? We don't design aircraft to have a factor of safety of 2. That would be irresponsible. So those are much closer to 1. Bridges, we don't design those to be close to 1 at all, right? Because that would be irresponsible. And there are other manners of predicting failure as well, like cyclic fatigue, right? So we'll look at fatigue as well before we wrap the class. Yes, well, that's an even different problem. I still haven't wrapped my head around the fact that we are retrieving things from space to resend back. That's quite, SpaceX is doing some amazing things. Just because he has the money, he's not actually doing. Let's give SpaceX engineers that credit. Oh, okay, yeah. I mean, it is nuts, absolutely. And SpaceX engineers are doing some really cool stuff. Okay, so I think that wraps up in a buckling example. Does anyone have any questions for me? We're going to move on to failure theory, if not. Go ahead, Jesper.
My only question would be if you happen to have the solution for this in plane buckling as well.
I do not.
That's fine. Never mind.
Yeah, so what would be different for in-plane buckling? We already talked about how inertia would be different because base and height change. They swap. What else is different?
The end conditions would be different?
Yes, so C goes from 1.2 to 1 because it's pinned on both ends, so buckling becomes easier.
And the inertia is going to get bigger.
Yes,
right?
So the inertia gets bigger, the end condition constant gets smaller, the cross-sectional area is unchanged, right? Yeah. So, I mean,
That's okay. That's okay.
Work it out.
But I was just wondering if you had it available. But
my instinct is that the critical slenderness, which will change a bit. Wait, will it? Hold on.
yeah, it'll go down a tiny bit, right?
It'll change by a little bit. And then the actual slenderness ratio, I expect that to go down much, much further down, and we'd be in the Johnson's criteria most likely, based on the width of the part. It's much less slender in that direction.
I agree. Yes. I don't know whether that tells us whether or not it would be even close to having a buckling issue with the load, but
yep.
Okay, that's fine.
So, but yes, so that would be the means of solution or method of solution. Okay, so so let's talk about failure theory a bit, because I really rushed through it the other day. And so I'm just going to remind us where we're at in the theory. And since this is right here, I'm going to do this rather than try to find slides. So I want to remind everyone, it's a little blurry. that what we're trying to do is describe failure in, right now we're looking at ductile behaviors, and we're looking at ductile material that has similar response in both tension and compression. And so there are materials that are going to respond differently in tension than in compression. They're going to have a different type of strength value. But for those materials that have similar tension and compression strengths, we have two straightforward failure theories. One of maximum shear stress, which is the theory that the maximum shear is the better predictor of failure than maximum normal stress. And that's a conservative value because it's an overestimate of failure. It overestimates the likelihood to fail. Distortion energy theory compares the strain energy at a state to the strain energy at yielding, at failure. And so this requires, so this assumes, no, this uses that strength, that yield strength, to establish a yield strain energy and compares the strain energy in the stressed area to that. And it's a less conservative value in that it's closer to the true failure point. And so let's look at that. Okay. So they got some really cool examples of failure in the book, and I could spend all day. But a quick reminder that we are going to use stress concentrations as we think about failure, because we all design things with holes in it. We all design shafts that have shoulders. There's lots of reasons why we're going to need to take a look at stress concentration factors. So don't forget that those will not only increase stress because of a change in geometry, right, the smaller diameter, etc., but also because of these concentration factors due to the discontinuity. And so what we're looking at for maximum shear strength theory is A, assuming that maximum shear strength is half of the yield strength. So SY is the normal yield strength, right? SY is in the axial direction. And so if—
Is that generally in tension or in compression? Or the same?
What we are talking about, it's the same.
Okay.
It is not the same for all materials.
Okay.
But for maximum shear stress theory, this only applies to materials for which compression and tension normal strength is approximately the same. So SY is our axial strength, and the yielding is predicted when the maximum shear stress exceeds half of the tensile strength. So to say that another way, our factor of safety for our maximum shear strength, maximum shear stress theory is equal to half of the yield strength, which is assumed to be our, so this is half of the axial yield strength. So this is our shear strength compared to the maximum shear stress in the critical area of the object. So that would predict failure if they were equal. Yeah, so this is maximum shear stress theory. So let's take a look at an example. And let's keep in mind also that this assumes, no, this lives in 3D, right? You don't have an actual planar element. So even when we're only stressing in 2 dimensions, we have a third dimension where the stress may be 0. And so I'm going to grab just an example out of the book where we're dealing with hot rolled steel. So we're given a strength. And we're given a stress element where we're told that sigma x equals 100 megapascals and sigma y equals 100 megapascals. And so that results in a stress element here, right? That looks like this. And it assumes that, yeah, I guess, so my question for you is, in order to say I know what tau max is, I need to evaluate my principal stresses. So I need to find sigma 1, sigma 2, sigma 3, and tau max. How do I do that if this is my stress element?
More circle?
Yeah.
Question mark?
Sure.
I mean, I'm sure there's some equations that could be used without drawing circles, but
Yeah. Could you immediately tell me what sigma 1 is? Just off the element?
sigma x?
Yeah. Why?
No x. Because it's the axial stress in that direction. And so it's going to be well, assuming it's greater than y, right?
So y, why, y is sigma x equal to a principal stress?
Oh, because there's no shear on the element.
Because there's no shear on the element.
There it is.
Yep.
Figured it out.
So sigma 1 equals sigma 2 equals sigma equals 100 megapascals because they're the same here. So what's sigma 3? Someone else.
Is it 0?
It is 0, yeah.
Wait, hold on. Why are 1 and 2 the same? Did I miss something?
Because sigma 1, yeah, x and sigma y.
Oh, okay. I see.
Yeah, it's just the way the problem is declared.
Got it. Okay.
They're not always the same. In fact, they're rarely the same.
I'm seeing now. Okay.
Yeah. So what we're saying is we have a Mohr's circle here where we have both sigma 1 and sigma 2 over here at 100 and sigma 3 over here at 0. And we're just going to draw this circle. And so I want to know tau max. So tau max here gets pretty easy. Yeah. Maybe, maybe not.
Oh, it's 50.
It's
Is
50.
it not?
Yeah, it's 50. Okay. So tau max is 50. And I was told that the strength is 350. So we're going to get another whiteboard maybe. Yep. So I know the yield strength is 350. The tau max is 50. These are both MPAs. So what's my factor of safety according to maximum shear stress theory?
Is it 3.5?
It is exactly 3.5 because we're going to take.
Yeah, whatever 350 over 2 divided by 50 is, right?
Exactly. Okay, so that's it. It's very straightforward. It's also an overestimate most of the time. In this particular case, having worked through it once now, it is the same as our distortion energy theory. We'll look at a different example where they vary. So that is maximum shear stress theory. That's it. That's all it is. 239. We're doing great. Okay. So yeah, so we're talking about equations 5.1, 5.3, pretty straightforward. Keep in mind that we need all three principal stresses, and we always order them from biggest to smallest. So sigma 1 is the largest on the number line, right? So even if sigma 3 is bigger in magnitude but it's negative, it's still sigma 3. We go from right to left on the number line as we order them, okay? Okay, so let's talk a little bit about distortion energy.
Hold on 1 second.
Oh,
Can you go
please.
back to that slide for a second?
I can.
What are those cases that it's talking about at the bottom there? Are they something that we need to worry about?
Oh, yeah, no, it's just stating, so it's, if you use your brain, you don't need these cases, but let me just explain them real quick. So it's saying that there are situations where you're going to have sigma 1, sigma 2, and sigma 3. You could have sigma 1, sigma 2, and sigma 3. And then, right, so these could be in different orders, and they could get on either side of the y-axis, is what it's trying to get at.
Okay.
And it's just trying to help you through those. But
Okay.
if you understand fundamentally that sigma 1 is always the farthest to the right, and sigma 3 is always the farthest to the left, and sigma 2 is always in the middle or equal to sigma 1 or sigma 3, right? Like those are your options. Then you can draw your circle and think about where tau max is.
Okay.
Yeah, so the
Not
reason
super important.
no, so the reason it changes, right, is so for my green circle, I have 1, 2, 3, right? So tau max is this one out here. For my blue circle, I would have 1, 2, 3. So that behaves much the same. So I have this one out here. But the one we just solved had, so there are other options here. We just saw one where we had 1, 2, 3. So there was only really one circle. So it's just describing the different cases for these circles.
Okay, that's fine.
Okay.
Thank you. I was just wondering if it was something that we should be looking at.
Yeah, it should be, for me, trying to break these down into too many rules and too many equations, I think actually complicates it rather than simplifies it. So
Fair enough
yeah,
to
I
me.
kind of skimmed over that. Okay, so let's talk about distortion theory. So as we are stressing an element, it is distorting. We know that. We know that we're in the elastic region. The stress and strain are related by Hooke's law and Poisson's ratio. And so this is not news to us. We have studied this. So when we think about how much the element is strained, we write the stress out in 3 dimensions. And 3-dimensional stress is a function of 3-dimensional strain and vice versa. So what I actually wanted to say was 3-dimensional strain is a function of 3-dimensional stress. So we have epsilon x, y, and z, and each of those is a function of all 3 stresses, right? And so the energy stored in that unit volume of material is the sum of the area under the curves in each direction here. So as we think about principal plane 1, 2, and 3 that are all perpendicular to each other, right? So we have essentially, if we're, you know, X, Y, and Z, and then a principal plane, X, Y, Z. So we're going to, just like we did in chapter 4 when we talked about strain energy and we took the area under the curve for force and deflection, right? So we drew this force deflection and we took this area under the curve, which is 1/2 F times delta. Here, we're taking the stress strain curve and doing the same thing, and this is my U. So 1/2 epsilon sigma, okay? And so that's the crux of the theory. It is just saying that I can evaluate the amount of strain energy, where is it? We can evaluate the amount of strain energy in a test specimen as it's yielding. And if I can specify the amount of strain energy in a specimen as it's yielding, I can compare my actual strain energy in my stressed element to that yielding strain energy. If I stay below it, I have not yet approached yielding. Does that make some sense?
Could you explain it one more time? Sorry.
Of course. So if I know that this is my strain energy at yielding, and this is where, or I've hit something, so it doesn't work very well on a diagram, because the point is there are 3 dimensions, and that's kind of the point, is if we compare a single force or single stress to a single strength, we're neglecting the fact that this is 3 dimensions. So if I know how much energy is stored at yielding, and I stay under that in my actual, we're safe. And so
I think the less than sign is a little bit backwards there for what you just said, but I understand what you're saying there.
well, yeah, it is exactly backwards, Jasper. Of course it is.
Okay. I mean, you
did
said
write
it
that
as
down?
you were
I said
writing
it
it.
right.
That's okay. Yes. Okay.
And
Okay.
then I didn't write it right.
So if
okay.
we're less energy in the deformation, we can assume that we haven't yielded yet.
Yes, exactly.
Okay.
And so we're going to take into account the fact that we have epsilon 1, sigma 1, epsilon 2, sigma 2. We have these 3 dimensions. So we're going to add up all of those areas to get our actual strain energy in our stressed element. And what distortion energy tells us is there is a way to do that and compare to the strength. That the distortion energy for the specimen in terms of our yield strength is a function of the yield strength, the Poisson's ratio, and the modulus. So now we've done a ton of empirical testing. We know SY and nu and E. Those are material properties. Those are empirical material properties. So I can rearrange my actual stress energy to compare directly to the yield strength and be considering the distortion energy, the strain energy.
There's a whole bunch of subscripts that are going on here that don't quite match what you've written on the board. And so can you just kind of explain what the different subscripts are talking about in this book here?
Oh, yeah, I'm sorry. I didn't use D.
So is D the
I
Y?
was trying to match Y, because
Okay.
that felt intuitive to me.
That's what I figured it was saying. Okay.
Yeah. And I can't modify these. And so, oh geez. Oh my God, it launched Explorer. Who even knew I still had that? Wow. Okay.
So then that final equation 510 down there is what you were saying.
Yes.
It eliminates the stuff cancels out essentially.
Right.
So we're comparing directly to the yield strength.
Exactly. And so the crux of it, the fundamental piece of this, and I don't think that the derivation is useful, right? We let lots of old people do the derivation, so let's use it and move forward and understand. What the derivation does is it takes all that strain energy of my actual condition and all the strain energy at yielding, and it substitutes in so that I can compare exactly my principal stresses in a particular organization to my yield strength. And so my factor of safety is the ratio of these two. And let's give this a name. That's my von Mises stress. Okay, and so that's what we'll do. We will call this left-hand side here, sigma prime, the von Mises stress, and we'll compare von Mises stress to strength to describe a factor of safety.
Yeah, you just said something about comparing them for a factor of safety. What exactly are we comparing for factor of safety?
Yes, yes, yes. Let me write it out. Because in all of that, I don't think it actually. So we describe von Mises as sigma prime. So then my factor of safety for distortion energy theory is my yield strength, all of it, because now we're talking about a normal stress. We're talking about a principal normal stress. So we're going to compare the yield strength to the von Mises stress.
Interesting. Which is the whole subtraction of the principal stresses squared.
We'll write all those out. Yep.
That's okay.
So the von Mises stress is a description of it. It comes from the strain energy in our actual element, right? It comes from how much strain energy has been stored in our element, but it is substituted and rewritten in a way so that it's a function only of the normal principal stresses. And as long as it stays below the yield strength, we do not predict failure. This is less conservative because it is closer to reality, right? So we're not overestimating the way we were with maximum shear stress. So, let's use our previous scenario, and we should either get the same factor of safety as MSS, or we should get a larger factor of safety. It should never be smaller, right? Distortion energy should always predict more margin of safety. Yes, I talk myself out of it every time, but because we're overestimating failure with maximum shear stress, the factor of safety goes down. Okay. Okay, so we said that the yield strength was 350 megapascals, sigma x was 100, and that's sigma 1, and it's also sigma 2, and sigma 3 was 0. Okay. And so our von Mises stress is equal to the square root, and we're going to take sigma 1 minus, and I can never remember the orders. Basically, you subtract each of them in turn, right? So it doesn't really matter.
And they're all added, so it shouldn't matter what order you do them in, right?
And they're all squared, right? So, yeah, exactly.
So it's just the 3 pairs, essentially.
Yeah. And you take the whole thing and divide by 2. And so sigma 3 is 0. So that's 0, and that's 0. Sigma 1 minus sigma 2 goes to 0, right? So sigma prime is going to equal 100 squared plus 100 squared all over 2. And now I'm really embarrassed. It took me at least like a minute and a half to stare at this the other day, but that's like 100, right? Because that's how maths. Anyway.
Yeah, it looks like that's 100 to me.
I think I had to take out a calculator. I was really tired yesterday. Okay, so so then my factor of safety for distortion energy theory would be SY over von Mises of 350 over 100, 3.5. So it's okay if they're the same. It's not okay if this was smaller than maximum shear stress. Questions, comments, concerns?
Go for it, Paul.
Wait, shouldn't the factor of safety for distortion energy be smaller? Or no, never mind. Nope, I see it now.
I do that every time I talk about it.
Okay, and then my question is, why are we dividing by 2 if we have 3 terms? It just,
You
it seems
divide
like,
it by 2.
I know, it must just be something in how it comes out to be. It's not like the Pythagorean theorem where you need to divide by the number of terms.
No. It's not an averaging at all. In fact, it's when you go back to distortion energy where we took our sigma and our epsilon and we found the area under the curve, that's where the half comes from. Is the 1/2
that
epsilon
makes sense.
sigma.
That
right?
makes a lot more sense than, yes. Okay.
So that's where the half comes from. Okay, so let's try a different example then, and let's do both. So we'll keep our hot rolled steel, so we won't change our strength. But let's see here. Excuse me. Okay, so let's say we've got sigma x equals -50. Oh, what happened? Oh no, that wasn't the one I solved. Hold on, sorry. Oh my. Okay, sigma x equals 100 and tau xy equals -75. And we're not told any other values. So we can assume sigma z, sigma y here are, well, sigma y is 0. And there's nothing going on in the z direction. Okay, so we'll do a more circle review because we need to get to our principal stresses. So either you're going to flip back to chapter 3 and look up your happy equations, or we're going to draw out a more circle, right? Right. So we have, it doesn't really matter which way I do this, but 100 and -75. We have 0 and +75. And I wanted to use contrasting colors here. So I have my diameter and I have my circle. It's not terrible. And I know that one of my principal stresses is 0. And what this tells me is my intermediate circles are going to be both smaller than the circle I just drew. So I have, so as I, and this goes back to one of those case things there, Jasper, right? Is my maximum tau is the blue, is on the blue circle. So I don't have to evaluate the purple circles, right? I always want to know in a 3D circle if I've got the biggest circle. That makes sense. I've got 3 o'clock brain on, so my words are starting to fall apart.
No, I think that makes sense.
Okay, so.
And it doesn't exactly look like it, but the center of the blue circle is where the dashed line crosses the x-axis, correct?
Yes, yes. Okay. Things are a little lopsided here.
That's fine.
Yes.
That's fine. Just making sure.
So this is sigma average. This is sigma 1. This is sigma 2. And this is sigma 3. And that's what I mean by right to left. So sigma 1 is always on the right. Sigma 3 is always on the left. Sigma 2 is in the center.
Is that dotted line just from the y-axis to sigma average?
It's the diameter. It just doesn't look like it. Oh, it looks less like it now.
Oh, okay.
Yep, circles aren't happening today, folks. I'm sorry.
And that's generated from the 2 known points that we have from sigma x and sigma y and tau xy.
So we have, this is x and this is y. So sigma average, oops, I'm off the screen. So sigma average is in the center of sigma x and sigma y. So it's at 50 megapascals, okay? And the radius of that circle is the length of one side squared plus the length of the height squared, square rooted, right? Pythagorean theorem here. So we're going to have, it's sigma average squared plus tau xy squared square rooted. If my writing is ever so sloppy, you're not sure what I wrote, please just say so. So it's the square root of 50 squared plus 75 squared. And that gives us a number. I'm sure it's a very good number. It's 90, it's about 90. Yeah, I'm going with 90. Okay, so my radius, which is my maximum shear stress, is 90 megapascals. I can say that sigma 1 is 50 plus 90, which is 140, I think. And then sigma 2 is 0, and sigma 3 is 50 minus 90, which is negative 40 maybe. Please do correct as you see it. That scribble is a
Looks
unit.
right to me.
Okay, so I'm just going to circle what we need to take away from this more circle. Oh, huh. Okay, so we have tau max, we have sigma 1, sigma 2, and sigma 3. So that was the whole goal here. Did I lose anyone? The goal was to get my principal stresses and my maximum shear stress. If I lost you, let me pull you along now. Okay, on we go, onward and onward. So I want to evaluate my 2 factors of safety. So I know my yield strength is 350. I know my maximum tau is 90. I know sigma 1 is 140. Sigma 2 is 0, and sigma 3 is negative 40. Okay, so that's what we know. So now I'm going to pause. I'm going to let you think about factor of safety for MSS, maximum shear stress, factor of safety for distortion energy. Be quiet for a minute while you make some thoughts. So let's start with the easy one. Factor safety, MSS. What do we got?
I got 1.94.
Who else? 1.94. Does that hold up? Paul got the same. So we took the 350 over 2. We divided by the 90, and you get that 1.94, right? Okie dokie. Robert and Ryan agree. Anyone with questions? Okay, so let us continue onward. What do we do to get distortion energy factor of safety?
Big boy time. All the parentheses.
All the parentheses. We're going to find, what's that term called?
Von Mises stress.
we're going to find von Mises stress. So we're going to take the square root of sigma 1 minus sigma 2 minus sigma 3, sigma 3 minus sigma 1. Take the square root, don't forget our half. So we're going to get our von Mises stress. So here, sigma 2 is my 0. So I'm going to go ahead and cross those out so I remember. So we get 140 squared. We get 40 squared, because signs don't matter what you square them, right? So I'm being a little sloppy. And then you get 180 squared all over 2 inside the square root. And it's a number, and it's probably a beautiful number. Probably not super round.
I got 2.14, I guess, round it to 2 digits.
For your factor of safety, I presume.
Yeah, sorry, yes.
That's okay. So I'm going to stop here.
That was all kind of subtracted in my head, so that could be wrong by a little bit.
Okay. I didn't, it's already gone. So can you say it again?
2.14.
Yeah, it sounds right. Okay. So I have my von Mises stress. So this is my von Mises stress, the good predictor of failure. So my distortion energy factor of safety. Whew. Okay, yield strength over von Mises, and that is 2.14. So if I look at my distortion energy and compare it to my more conservative MSS, my shear stress theory, that's telling me it's going to fail earlier. That's more conservative. It's predicting an earlier failure. I can, and they're not hugely different, right? We're talking about a difference of 0.2, which is about 10%. So they're just alternate theories, and we'll see different loadings have different discrepancies.
I was just going to ask that.
Yes.
It must depend on the situation.
100%, yes.
Okay.
Okay, and so that's where we're going to wrap maximum shear, failure theory, at least of all because my brain and my mouth are getting disconnected, but how do I stop?